So up until now, we've been talking about motion on one dimension, and it's all been on the x-axis. So we have dealt with what as our change in position? Delta x. Yeah, that's easy. Yeah, you're like, oh, I knew that. That's what you meant? Yeah. Well, now we're going to take everything, and we are literally going to turn it 90 degrees. Ah! It does freak some people out, I'll admit. And now, instead of delta x, guess what we're going to talk about as our change in position? Delta y. And yes, you have to make the switch. Every year somebody asks this. They say, well, can't I just keep calling it delta x? No. Reason being, in Chapter 3, we will have lots and lots of problems that have both a delta y and a delta x component, and you will be solving for both of them. So you got to make the switch. You have to just think about it in terms of the Cartesian coordinate system that's imprinted on all our brains somewhere in the 4th to 7th grade. We start seeing the world in that little Cartesian model. So when we're talking about change in position on the y-axis and basically motion on the y-axis, we get into the idea that there is acceleration on the y-axis frequently, and there is really only one acceleration on the y-axis. And that acceleration is negative 9.81 meters per second squared. And this is a number that you will remember, use every day. So this person who's skydiving, plunging towards the earth, when we subtract out air resistance, their acceleration is, guess what? Negative 9.81 meters per second squared. When we throw a ball up in the air, as many of you have recently, guess what its acceleration is? Negative 9.81 meters per second, oops, I can't even write an S, per second squared. As it's on its way up, guess what its acceleration is? Negative 9.81 meters per second squared. As it's on its way down, guess what its acceleration is? Negative 9.81 meters per second squared. At every single moment that it's acting under the influence of gravity alone, its acceleration is negative 9.81 meters per second squared. Period. Unless there's a rocket pack strapped to it. And then it's a whole different problem. Oops. So, to drive the point home in the most irritating fashion possible, and this is... so, if these turkey poults, or a chicken, or a chipmunk, or a cow jump off of something, what is their acceleration? Negative 9.81 meters per second squared. If an elephant jumps off of a shoebox, on the way down, its acceleration is negative 9.81 meters per second squared. If I throw this pencil up in the air, its acceleration the whole trip is negative 9.81 meters per second. Okay, we got it, Moses, shut up. So, that's a number we're going to be working with a lot. Here's the thing that we have to be really careful with. Sign in these problems stands as a proxy for direction. And we've kind of already talked about this, but we're talking primarily thus far about problems where we say, well, this is our arbitrary zero mark, and that direction's positive, and that direction's negative. That's what we've been doing. Sort of using that imposed Cartesian coordinate system. Now, we're starting to talk about things where up is positive, down is negative, which we've already talked about. And it goes hand in hand with, like I said, the Cartesian coordinate system was stamped on your brain at birth. Okay, not at birth, somewhere in, like I said, 4th through, I think you start graphing in 3rd grade. Yeah, so maybe like stamped on your brain in 3rd grade and reinforced ever since. This is a convention. Is the down direction actually negative? Is there some negative sign out there in the world? No, this is a convention we make up and we impose on the world so we can figure out how the world works. The world is more complex and wondrous than we can calculate. But to simplify the world for calculations, we call things hurtling towards the center of the earth down, things flying up towards the top of the atmosphere up. That's easy. G. this is where your book and I diverge, other than on sig figs. Other than on sig figs, I love the Holt Modern Physics. I think it's a good book. I think it lays out the concepts that you need to master in a logical fashion. I think it's a very well-written textbook. I like it. There are two places where I diverge from the book. One is their handling of sig figs and a lot of problems. They get it wrong a lot. And like I said, I doubted myself. I checked myself. Nope, I'm right. The book is wrong. They do a bad job with sig figs. The other one is how they handle gravity. So when we're talking about acceleration due to gravity, and you will sometimes see that written as A sub g, it's a negative because it's down towards the center of the Earth. One of the things your book does is it takes all of these problems, and of course we're going to swap out the delta x for a delta y, and it says, well, when we're dealing with acceleration due to gravity, it actually changes these problems and says 1/2 g delta t squared. Why is that delta t sub 2? Don't know. I don't do that. I've never done that. I actually find it more cumbersome and more confusing to do the swap out that they do. So they would have you write a whole new set of golden equations, substituting in g. I think you're smart enough to know that if we're talking about acceleration due to gravity, that's negative 9.81 meters per second squared. For now, because we're only dealing with one axis at a time, you can continue to just write acceleration, and when you're listing your variables, write negative 9.81 meters per second squared. When we get into the next chapter, we have to specify which axis variables are on, but we'll cross that bridge when we come to it. There are ways to denote that. So anyway, their treatment of gravity is a little bit different. I typically just list my variables, acceleration, knowing that it's from gravity, negative 9.81 meters per second squared. If you want to delve into how they do it, you can. I find overall my method is much simpler. There's one pitfall to my method. There's one problem in chapter 4 that algebraic, the sign stuff gets weird my way and it doesn't get weird their way. But I can sacrifice one problem for overall ease of problem solving. That's the compromise I've made. So with that, let's get to some problems. So the problem we're given, Jason hits a volleyball so that it moves with an initial velocity of 6 meters per second straight upward. If the volleyball starts 2 meters above the floor, how long will it be in the air before it strikes the floor? Assume that Jason is the last player to touch the ball before it hits the floor. So the ball is 2 meters up. It's up here somewhere, and he hits it straight up. How long does it take for that ball to hit the ground again if nobody else touches it? The first thing we're going to do, obviously, is list all of the variables that we've got. We have a VI, and I'm going to put the plus sign in there just as a little reminder to self, of 6.0 meters per second. We have a delta Y. What's our delta Y? Okay, you've got it half right. Let's draw this. Here's the floor. Here's where the ball is starting. Where's the ball ending up? The floor. So the magnitude of the displacement is 2 meters. It's negative 2 meters. So the displacement is negative 2.0 meters. That's one of those things that you have to be really aware of in these problems, is thinking about that displacement. It's not a big problem unless you got an issue where you're taking a square root, and then you're going to end, if you forget that, you're going to end up with a negative under a radical, and you're going to go, something's wrong. And that's generally one of the first things to check is, did I get the sign on my displacement correct? So, good. So we've got a VI, we have a delta Y, we have acceleration. What's the acceleration? 0.81 meters per second squared. You got it. Let me shrink that so I can get everything in. Okay. What do we want? Time. We want delta t. Now, have I mentioned yet, I think, for the 100th time, that there are probably 6 ways to solve every physics problem. 5 of them will give you answers, and 2 or 3 of them will give you correct answers? There are multiple ways to solve this, and if you grab your note card, do we have any equation that ties these 4 variables together? Yep. And we would, of course, say it was delta y, vi, delta t, 1/2 a delta t squared. There's a problem there. Anybody see it immediately? Whoa. So if we use delta y equals vi delta t plus 1/2 a delta t squared, what variable are we solving for? T. Unless the vi is 0 and this goes away, which it doesn't in this case, that means that what kind of solve would this be? How do you solve an equation for a variable where you have that variable twice and one of them is squared? Well, actually it's worse than that. I don't know that there's a way to solve it just through factoring. It's a quadratic solve. Ouch. Can it be done? Yeah, it can. There are a couple problems in some of the handouts where that's really the only way to solve them. I try to avoid the quadratic solve if at all possible because, quite frankly, the quadratic equation gives me hives. I love algebra, and as much as I love algebra, I hate the quadratic equation. I can't explain why. Is there another way to solve this? Yes. So let's call this, way number 1 to solve this. Like I said, there are probably 6, and 5 of them will give us an answer. Is there an easier way? Yes, there is. Are there any other things that tie together some of these? Yeah, a whole bunch of them. So if we had VF, we could use this. Doesn't account for acceleration. If we had VF, nope, that doesn't give us time. We don't want that. If we had VF, heck, we could just use that. That's simple and beautiful, so we don't want that because it doesn't give us time. But either of those 2 upper equations look promising if only we had VF. So remember how I've said I would discourage you from doing sort of double steps where they're not necessary, where, don't rely on your own numbers to calculate. Is there a way to do this without doing that? Yes. And it's a way to do it that sets you up well for practice in what we're going to do in Chapter 3. The part of Algebra 2 that physics uses most heavily is the substitution part, creating expressions, subbing them into other equations. So you're building more complicated expressions. It sounds scary. I see some of you looking like you're facing, a cornered possum in the garage, but it's not as bad as a cornered possum, I promise you. We keep saying if only we had VF, because we want to make sure that we have this rate of acceleration accounted for, because that rate of acceleration is really important. So do we have something that would tie together VF, VI, delta y, and delta t? We do. We have this guy, and we initially threw it out because we don't have time. But we can build an expression for VF out of that, and then substitute the expression for VF back up into this problem, or into this equation. So, let's do it. Okay, so let's use this bottom equation, VF squared equals VI squared plus 2a, and in this case, of course, it's going to be delta y. How can we solve that for VF? Boy, this one's simple. I don't know. There's something. Take the square root. Okay, so VF is equal to the square root of VI squared plus 2a delta y. That was easy. We now have an expression for VF. Do we have VI? Yes. Do we have acceleration? Yes. Do we have delta y? Yes. Cool. And I'm actually going to write that up here in my list of variables. VI squared plus 2a delta y. And I'm just going to count that as, now that is one of my variables. Now, having an expression for VF, having a way to achieve VF, do I have an expression that ties together VF, VI, and A delta t? I do. So we're going to do this. VF equals VI plus A delta t. I want to solve here for delta t. So VF, whoops, geez Louise Moser, minus VI equals A delta t. Let's shrink that. VF minus VI divided by A equals delta t. Well, that's beautiful. That's not so bad. And now all I have to do is take this expression and substitute it in for VF. Now here's the really beautiful part about this. When you do that, let me shrink a bunch of stuff. When you do that and you put your substitution in there, so I'm going to use brackets here because they're easier for my brain to comprehend in a complicated world such as this problem just became. What we've created is an expression that ties together all of the original things we had. It ties together VI, there and there. It ties together delta Y, there. It ties together A, there and there, and gives us a solution for delta t. So we took the four golden equations and we basically created a fifth equation out of them by doing a substitution. We do a lot of this in Chapter 3, so it's a skill to practice. Your book does this differently. Your book actually solves for delta t and then takes that value and plugs it back in. I think, and can you do it that way? Yeah. Is it any inherently riskier than doing this? No, because in essence you're doing the same thing. You're doing this entire calculation in the process of doing this problem. So it is 6 one, half dozen the other in a way. But gaining the skill of creating the expression really serves you well as we move on. And again, this is where, like, this is algebra boot camp. This is one of those things that really beefs up your algebra skills because you start to see how to do this. So let's do some plugging. Okay, so plugged in it looks like this. We have the quantity of square root 6 meters per second, quantity squared plus 2 times negative 9.81 meters per second squared times 2 meters. And then that entire quantity, subtract 6 meters per second, divide by negative 9.81 meters per second. Do you see the places where if you didn't have your displacement as negative, you would have an issue? One of the things that I do find helpful, that I do for myself, because especially when you've got a long, complicated string of calculations, is I'll make a note to myself, hey, the quantity that I got under that was 75.24. You don't have to do, you don't, for me anyway, have to write down in these kind of problems all of your little intermediate values, but you can, for yourself, sometimes it leaves you a useful breadcrumb trail so that you can then go back and recalculate chunks and see if you see where you messed. I have my intermediate value there of 8.67 blah blah blah, minus 6, I get 2.674 blah 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 blah. What are my units there? I had meters squared over seconds squared, square root, so that's meters per second on the top, divided by negative, be careful, Moser. Hey, be very careful. I just screwed something up. Who caught my mistake? What did I forget to account for? What's my foot in the mouth moment? So so you have to remember that this quantity here is your VF. What value did you get? 8.67 something. What direction is this ball traveling when its final velocity, when it hits the ground? down. Square root gives you an answer that is what? Plus or minus. When we take the square root, we don't know if that's a positive of that number or a negative of that number. So you have to mentally say, oh, well, this is, plus or minus. That's going to be negative 8.674 ... So I'm going to take my 8.674 on the calculator. I'm going to do the negative of that number. Then I'm going to subtract 6. So for the numerator, I get negative 14.674 blah, blah, blah meters per second. Not that 2. I'm going to divide that by acceleration due to gravity. Divided by negative 9.81. You got to run. Okay, did anybody get 1.4958, etc.? Yeah, sorry. Yes. So a note about my sort of, wouldn't be nomenclature, my crazy methodology. I don't know what it is. With the TI multi-view calculators, because you can carry larger numbers down, I usually don't write the entire long number. What I'll do is write, the first 2 or 3 decimal places, and then I'll put a ... in to remind myself that there's a larger number there, so that I don't punch in 14.674 and think that's the whole thing. And then I just pull it down on the calculator. If you're not comfortable pulling numbers down on the calculator, or if you're using one of the graphing calculators or some other calculator where you can't do that, I would literally write every single digit out to the limit of your calculator, just because you don't want to have rounding errors. So.
Because I used the first equation we were going to use, and I solved for it, and I got a number.
Did you do the quadratic?
No.
No? In the book, that they sig fig it out to 1.50. Oh, actually, okay, our sig figs, our rounding agrees. Do we actually have, oh no, we don't agree, because we only have how many sig figs? 2. So final answer on this should be 1.5 seconds. Okay, do we want to walk through any of that process and any of the little foible thingies? No? Okay. Let me ask you this question. When I said, oh shoot, I screwed up the final velocity, what tipped me off? What was my clue? Anybody know?
Your time was going to be negative.
My time was going to be negative. And I suddenly realized, I did something wrong. So here's the answer, and it's not a nice one. Sometimes when time is negative, it's no big deal because it just means you have a sign error and it doesn't change the magnitude. Sometimes when time is negative, it's a really big deal and it changes the magnitude of your answer. So here's what you do. Anytime you get to the end of a problem and you realize that, oh shoot, I'm coming up with a negative time, what that says to you is you have to walk backwards through the equation. And just having a negative time doesn't tell you if it's the kind of error that will change the magnitude or the kind of error that doesn't change the magnitude and you just have a goofy sign and you can kind of ignore that. But it's a red flag to you that you have to walk back through every step of your calculations and all your assumptions. In this case, it was easy for me because I was like, oh, wait, final velocity would be negative. This thing is heading down towards the center of the Earth. But it's just anytime you come up with a negative time as an answer, when you see that you're headed for that, that's a clue to you. You got to go back and recheck stuff. And you'll get really good, actually, at separating out the kind of errors that change magnitude and the kind of errors that don't. I promise you will get good at that. Okay, questions, comments, concerns? Here's my plan. You group the desks up. You work on the 2F on page 64. I haven't gotten the worksheets printed yet. I'll have those for you tomorrow. You work on those. I'm going to float around and check in on you. And if people feel like they were a little bit left in the dust, I'll walk through any steps of this with you that you want. And that's the rest of our agenda for the day. Cool? Okay.